and welcome to our module on physical layer security. Let's start with a brief outline for today's talk. We'll start with a brief recap. We will talk about practical wireless scenario in the context of physical layer security. We will then talk about secrecy capacity of wireless channels. We will define outage capacity, talk about outage probability, and then look at some practical schemes like cooperative jamming, artificial noise forwarding, and friendly jamming. So let's start with the basic idea about secret communications. As we have observed earlier, there are two ways to do secret communications. Either have a hard mathematical problem to solve, which the eavesdropper or the adversary will take time and computing resources to solve, or use the inherent noisy nature of the channel and provide security at the physical layer. This lecture concerns with the second approach, how to use the inherent noisy nature of the channel and provide information theoretic security. So, a quick recap. What we have assumed so far is that secret key is available only to the transmitter and receiver, and the secrecy in classical cryptography is based on solving a known difficult problem using finite computing and time resources. But we have also observed that computing systems are becoming more and more sophisticated, networked, distributed, and the threat is genuine. In the last lecture, we had talked about Shannon's notion of security, where Shannon assumed that both the main channel and the eavesdropper channel was noiseless. However, they had the same shared key k, which was used to encode and decode the message. And what Shannon said is that for perfect secrecy, h of m given z, entropy of the message m given the observation of the eavesdropper z, is nothing but h of m. That is, no information is conveyed via z. Z does not contain any information about m. So, the block diagram looks like this. M message goes to the encoder using the key k is encoded into z, which is decoded using the decoder using the same key k and gives back m. No noise anywhere in the channel. The eavesdropper has his hands on z, and his job is to find out m from z. So, I of m semicolon z, the mutual information between the message and the observation of the eavesdropper, is nothing but h of m minus h of m given z. And what Shannon suggested is that the I m semicolon z should be equal to 0 for perfect secrecy. What it means is perfect secrecy is achieved if code word z and message m are statistically independent. Now, for the case when both the key and the message are binary, we have the message m, we use the XOR function, we get another binary stream which is XORed back with the key k, and we get the message. And eavesdropper uses this binary version. And what Shannon had shown is for perfect secrecy, we should have h of k, the key, should be greater than or equal to h of m, the message. That is, the key should be at least as big as the message. And this was achieved using one-time pads proposed by Vernon. We had also looked at the wiretap model, which was initiated by Weiner almost 25 years later. And here we have the source. It goes through an encoder which generates x of n. So, n is the block length of the code, which is sent over the main channel. But this main channel is noisy. This is the first assumption made by Weiner, and what we get is yn, which is decoded back. Now, this may or may not be always correct because there is a finite probability of error. On the other hand, there is a wiretap which is also noisy, and the eavesdropper gets zn. So, the two relaxations made by Weiner are the noiseless communication assumption, where Weiner assumed that the noisy main channel and noisy eavesdropper channel is present in the system, And the second assumption is the relaxation of the perfect secrecy condition, wherein he said that the normalized leakage of information I m semicolon Zn normalized by the block length n should tend to 0 as limit n tends to 0. N here is the block length, m is the message, Zn is the observation of the eavesdropper. This is the weak secrecy constraint as opposed to the perfect secrecy assumption made by Shannon. Then we had looked at strong and weak secrecy, and the strong secrecy condition we had observed is the mutual information between the message and the observations of the eavesdropper tends to 0 as n tends to infinity, and the normalized mutual information 1 over n I m semicolon Zn tends to 0 as the weak secrecy condition as n tends to infinity. We had also defined equivocation rate as normalized h m given Zn, normalized by the factor h of m, the entropy of the message. We have to also look at the two objectives to be satisfied. One is that of reliable communication. So, at a reasonable transmission rate, we should have probability of error tending to 0, and then we have the requirement for secret communication at a reasonable equivocation rate delta. Therefore, we had this pair, and we talk about weak rate equivocation pair R comma R sub E. And here we have these two conditions. One is the reliability condition, the second is the weak secrecy condition. The first one, limit n tends to infinity, probability of error for a code word goes to 0, and n tends to infinity 1 over n, the equivocation as a function of the code word should be greater than or equal to Re. Note, both these conditions may not get satisfied simultaneously. Now, we also defined rate equivocation region last time, where the weak rate equivocation region for the degraded wiretap channel is given by R as the closure over the set R comma Re, where R comma R sub E is achievable. So, we made the observations that the rate equivocation pair R comma Re is achievable, then the rate pair R comma Re prime is also achievable if Re is greater than or equal to Re prime. And clearly, rate equivocation pair R comma 0 is always achievable. We had also defined secrecy capacity as the maximum possible transmission rate for which the eavesdropper is unable to decode any information. What does it mean practically? Secrecy capacity is the maximum rate in which the secret information may be sent to the receiver under perfect secrecy. We had also defined secrecy capacity of the degraded wiretap channel as the difference between the mutual information I x semicolon y and I x semicolon z, where maximization is over the input probabilities. This is the secrecy capacity of a degraded wiretap channel. We had also explained that if we have the luxury of both the main channel and the eavesdropper channel as weakly symmetric channel, then the secrecy capacity of a degraded wiretap channel in this special case is Cm, the capacity of the main channel, minus Ce, the capacity of the eavesdropper channel. Please note, both the main channel and the eavesdropper channel must be weakly symmetric channels for this to happen. Then we talked about the Gaussian wiretap model. It was proposed by Cheong and Hellman, and the assumptions were that the main channel and the wiretap channels were both independent and identically distributed Gaussian, and they had 0 means and variances sigma 1 squared and sigma 2 squared with an average power constraint of p. In this case, it was shown that the secrecy capacity is Cm minus Ce super plus, where x super plus is nothing but max of x and 0, so it is non-negative. The eavesdropper's channel is a concatenation of the main channel and the wiretap channel. Now, for the Gaussian case, it is easy to plug in the value of Cm, the capacity of the main channel, which is nothing but half log 1 plus power over SNR. So, this is the capacity of the Gaussian channel for the main channel, and here is the concatenation. So you have 1 plus power over sigma 1 squared plus sigma 2 squared. So the secrecy capacity Cs is given by the difference between these two channel capacities. Now let's look at the practical scenario where we have a transmitter in the room and we have a legitimate receiver, and before we realize we have an eavesdropper coming in. So this is a democratic setup, so both the legitimate receiver and the eavesdropper are free to move around in the room, and it could be possible that the eavesdropper is closer to the transmitter than the legitimate receiver. But we know that the channel quality depends on the distance between the transmitter-receiver pair, and so the relative qualities of the main channel and eavesdropper channel can vary. So it can be shown that if the main channel is more capable than the eavesdropper's channel, then the secrecy capacity is given by Cs is equal to maximization over input probabilities I, mutual information between x and y, minus I between x and z. Now note, both I x semicolon y and I x semicolon z are concave functions in the input distribution of Px. Hence the difference can either be convex or concave in the input distribution Px. Now it has been shown that in the event that P z given x is less noisy than P z given x, so z given y is less noisy than z given x, then we have I x semicolon y minus I x semicolon z is necessarily a concave function in the input distribution of P of x. So what do we conclude? If the eavesdropper channel is noisier than the main channel and both channels are weakly symmetric, in this special case the secrecy capacity is simply given by Cs equal to the difference of Cm, the capacity of the main channel, and Ce, the capacity of the eavesdropper channel. Now if the main channel is noisier than the eavesdropper channel, the secrecy capacity is clearly 0. Let us look at this practical example. So we have a transmitter and it is happily communicating with the legitimate receiver, and the channel, which is the main channel, is represented by this binary symmetric channel. Like it or not, we have an eavesdropper in the room and it has another binary symmetric channel represented as follows. Here the probability of error is small p, here it is small q. So the main channel is binary symmetric, the eavesdropper channel is binary symmetric, both of them are weakly symmetric channel. Now, assuming p is less than q is less than 0.5, we make the main channel less noisy than the eavesdropper channel. So we have satisfied both the condition about main channel being less noisy than the eavesdropper channel, and both channels are weakly symmetric channels. So clearly the secrecy capacity is easily calculated as the difference between the two mutual information, and we know that for this binary symmetric channel we have it is 1 minus Hp minus 1 minus Hq, and it is nothing but Hq minus Hp. So very simple expression for this scenario. Now let us consider the wireless scenario where flat fading occurs. So there is flat fading between the transmitter and legitimate receiver, as well as between the transmitter and eavesdropper. So how does the received sample look like? The received samples can be expressed as Zk is equal to this channel gain Hk Xk plus Nk, and Yk is nothing but the channel gain Gk Xk plus Ek. Hk and Gk are the time varying fading coefficients of the main channel and the eavesdropper channel respectively. The noise samples are represented by Nk and Ek, which are assumed to be complex or additive wide Gaussian with variance sigma m squared and sigma e squared respectively. So it is easy to calculate the average SNR at the legitimate receiver. It is given by this expression, and the average SNR at the eavesdropper is similarly given by SNR sub e with this expression. Okay? So we have this expectation of the channel gain times the power normalized by the noise power. So, the capacity of the main channel Cm is simply plugging in the values in the expression for the capacity of the Gaussian channel, because we are talking about the Gaussian channel here, and the capacity of the eavesdropper channel is similarly like this. Okay? But we have not made any assumption about the wiretap model here. It could be in general. So, the capacity is nothing but the difference between the capacity of the main channel and the capacity of the eavesdropper channel. Right? Please note the super x here, so it can be greater than or equal to 0. But the interesting observation is that h of k and g of k are both random variables. Consequently, Cm and Ce are both random variables. Consequently, the secrecy capacity is a random variable. So, it keeps fluctuating. So, can we use it to our benefit? So, Hk and Gk are time varying fading coefficients. Okay? So, whenever the SNR of the main channel is greater than the SNR of the eavesdropper channel, we have an opportunity to get positive secrecy capacity. So, let us talk about it in terms of a secure time slot S, and whenever it is less, the main channel is poorer than the eavesdropper channel, we should not transmit. So, it is an insecure time slot I. So, suppose we had the luxury to plot the received SNR of the legitimate receiver is the bold lines red, it is the received power of the legitimate, and the dotted line represents the SNR at the eavesdropper. So, sometimes the eavesdropper is better off, sometimes the main channel is better off. So, clearly whenever the signal strength and hence the SNR at legitimate receiver is better than that of the eavesdropper, we have the secure time slot S. If the things change, then it is an insecure time slot I, and then sometimes it is secure, insecure, and so on and so forth. So, we can use the fading channel opportunistically for secure communication. Now, let us define the outage capacity. First, an outage occurs if the secrecy capacity is smaller than a certain fixed value called outage capacity, and the outage probability for a certain outage capacity C outage is defined as a probability Cs is less than C outage. These are used to characterize and compare different secure communication schemes using physical layer security techniques. Now, consider a wireless communication scenario with a source, a legitimate receiver, and an eavesdropper. And it is a wireless scenario, it is completely democratic, the eavesdropper is free to move anywhere he or she wants to. So, in this example, we say that the transmitter and the intended recipient are such that their SNR is fixed to 20 dB. But suppose the eavesdropper is farther away from the transmitter as compared to the intended receiver, maybe sitting just outside the room and listening in. So, SNR at the eavesdropper is poorer, it is only 10 dB. So, you can plot the outage capacity as follows, the x axis versus the P outage on this side, and you can see that the outage probability versus the outage capacity for a fixed SNR of the main channel at 20 dB. Now, we will look at couple of practical techniques to help physical layer security. What is the motivation? So far, we have developed the intuition that higher the degradation of the eavesdropper channel, the better is the secrecy capacity. So, should we just rely on the channel, or can we do something to degrade the channel of the eavesdropper? So, we would like to introduce some interference or artificial noise in the eavesdropper channel without affecting the main channel. So, how can we degrade the eavesdropper channel without degrading the main channel? That is the million-rupee question. This has led to the idea of cooperative jamming, where the term jamming refers to intentional prevention of radio communication using electromagnetic signals. So, consider the scenario where we have a transmitter, which is our source, it sends information to our legitimate receiver R, and it's a noisy channel. So, Z1 is the noise being added. As always, we have our friend the eavesdropper sitting in the room, and it also receives signal, and the noise added is Z2. The idea is, can we have a friendly jammer who is only affecting the eavesdropper, but not the intended recipient directly? This is the basic idea about cooperative jamming. So, the jammer is adding additional interference to the eavesdropper's channel, thereby degrading it, thereby improving the secrecy capacity of the system. So, in this simple setup, Z1 and Z2 are 0 mean with variances sigma m squared and sigma e squared, and let the friendly jammer transmit also a Gaussian IID sequence with variance sigma j squared. So, we assume that the friendly jammer has quietly placed itself close to the eavesdropper and quite far away from the legitimate receiver, right. Now, we are not discussing the fairness of this assumption, but let us assume that it has been able to do it. Maybe it has a directional antenna, maybe it is using some technique, but this are the assumptions. So, we recall that in the absence of the friendly jammer, the secrecy capacity was simply Cs equal to Cm minus C, provided we had the certain conditions being satisfied. Here Cm is the main channel capacity, Ca is the eavesdropper channel capacity. So, when we have the cooperative jamming, the main channel is unaffected, but the eavesdropper channel has the noise power and the jamming power put together. And when we make P very large, then the upper bound on Cs, P vanishes, and we are left with half log in the numerator sigma e squared plus sigma j squared, where sigma j squared is the noise power introduced by the jammer, whereas sigma m squared is the noise power in the main channel. So, clearly the numerator is larger, and it can be made as large as possible depending upon how much power we want to give to the jammer, and cooperative jammer can improve secrecy rate. There are many ways to do cooperative jamming, and some of the ways are cooperative jamming with noise, cooperative jamming with random code, and cooperative jamming with structured codes. Now, if we have the luxury of multiple antennas, we can do cooperative jamming using that. So, our scenario is similar. We have our transmitter, our legitimate receiver, and the omnipresent eavesdropper is always trying to listen in. Of course, we introduced our new player J, which is a friendly jammer, and it has multiple antennas. So, multiple antennas allow you to radiate power differentially in certain directions. It can form a beam pattern, and it can direct the beam at certain directions. So, suppose this is the radiation pattern, and by changing the weights on the antenna elements, I can steer this beam. So, if my receiver or the eavesdropper move around in the room, my friend the friendly jammer can steer the beam accordingly. But what does it do with the beam? Well, it makes the radiation pattern such that there is a high gain in the direction of the eavesdropper, but there is a null in the direction of the legitimate receiver. So, very little of the jamming sequence is actually received by the legitimate receiver, but the maximum brunt of the jamming signal is borne by the eavesdropper, thereby degrading its channel. So, this is one of the simple techniques of cooperative jamming with multiple antennas at the friendly jammer. Another technique that can be used for physical layer security is called artificial noise forwarding. Now, the friendly jammer in the earlier example needs to know the channel between the jammer and the eavesdropper, or maybe the location of the eavesdropper, but it is not always available. Question is it possible for the transmitter to degrade the signal received by the eavesdropper without affecting the legitimate user? And this is possible by way of noise forwarding. So, noise forwarding is a technique in which the transmitter transmits an artificially generated noise along with the information signal. This artificial noise is generated in such a manner that it does not affect the received signal. most likely the legitimate receiver, who is our friend, should be able to cancel out this noise, but our eavesdropper will not be able to cancel it out. So we have a transmitter, we have a channel to the legitimate receiver with a channel gain, and we have a channel to the eavesdropper, and again, as before, we have additive white Gaussian noise. So here you can write the expression for the signal received at the legitimate receiver YR, which is basically the gain in terms of HTR ST, HTR NT, and Z1, which can be clubbed as follows. Right? The Z1 represents the noise at the legitimate receiver, but note that HTR NT, which is the jamming signal received, the artificial noise received at the legitimate receiver, is cancelled out because we have some techniques to cancel out the noise. Okay? So this is the artificially generated noise term. This vanishes from the expression for the legitimate receiver, but it stays put for the expression of the eavesdropper. So the eavesdropping signal receives the transmitted signal, the transmitted artificial noise, and its local noise. Okay? So the secrecy capacity again can be written as the difference between the main channel and the eavesdropper as follows. So we observe the following. The eavesdropper, if located very close to the transmitter, that is, if sigma e square goes to 0, this yields the minimum guaranteed secrecy capacity regardless of the location of the eavesdropper, because we have taken into consideration the worst case scenario that the eavesdropper is placed very close to the transmitter. So all the secrecy is provided by the artificial noise introduced by the channel. So we try to conclude this lecture with some applications. Please note that the broadcast nature of the wireless medium makes it very hard to eliminate unauthorized access to wireless networks. People can be standing outside the room and listening in. They can be sitting in cars parked outside the house and listening in office scenario, home scenario. It becomes very difficult to get rid of eavesdropping. Physical layer security addresses this problem. So this passive attack, eavesdropping, is primarily addressed by this physical layer security. If you look at the kinds of popular attack, we have the denial of service attack, resource consumption attack, replay attack, and message modification attack. These are the active attacks. Eavesdropping, on the other hand, is a passive attack, as is traffic analysis. So our physical layer security techniques are pretty much useful for eavesdropping kind of attacks. And techniques such as artificial noise injection, friendly jamming, etc. will help reduce wireless communication problems in terms of security at the physical layer. We are not making any assumption what kind of resources are available at the eavesdropper or how much computing power or time it has. Okay? So let us summarize this lecture. We started off with practical wireless scenarios and talked about physical layer security in real life wireless scenarios. We talked about the secrecy capacity of wireless channels. We talked about outage capacity and outage probability. These are used to characterize systems and compare systems using physical layer techniques. Then we talked about a couple of practical techniques. We started off with cooperative jamming, artificial noise forwarding, and friendly jamming. That brings us to the end of this lecture.